If you've ever thought that physicists were a bit silly to always be ignoring air resistance, also known as drag, well, today is your lucky day because you're going to find out exactly why we tend to ignore it, particularly in introductory physics courses. So, as I mentioned, we tend to call it drag as opposed to air resistance, but air resistance is fine. And this leads to another concept called terminal velocity. As you know, if you drop an object from a very high building or out of an airplane or something, it will not continue to accelerate all the way down until it hits the earth. It will reach a maximum speed, and we call that the terminal velocity. This is good news. Most of you have probably heard these types of things. Otherwise, rain would be coming down incredibly fast. I don't know the exact calculation, but anyway, we are going to look at how these things work. So typically, we say that our drag forces are either proportional to the velocity of the object, and that is true if you have small objects that tend to be fairly streamlined or objects at very low speeds. Other times we model the drag force as being proportional to the square of the velocity. This is more typical for something like a baseball or a car or an airplane or something like that. If we look at the full equation, the drag force is equal, let's just go with the proportional to velocity case. It's going to be something like this: 1/2 times the density of the fluid that you're going through, typically air, times the drag coefficient. You've probably heard of drag coefficients, times the cross-sectional area, times the velocity. This drag coefficient here is typically between 0 and 2. Things like the Tesla Model S has a drag coefficient of 0.24, and that is quite low for a car. Probably the lowest for any car that has been widely produced. Something like a brick, nice and rectangular, would have a drag coefficient somewhere in the neighborhood of 2, so that gives you an idea there. Now, the density of air is going to change as a function of pressure and temperature, so this gets a little bit nasty. We are just going to collapse all this stuff down and assume that it is constant, and so we are going to say we're going to ignore all this and just model it as some constant b times the velocity, and we typically throw a negative sign on there just to remind us that this drag coefficient is acting in the opposite direction of the velocity. Alright, so if we look at how this works out for a falling object, if we're looking at the net force acting on an object, that's always equal to ma. If I drop an object from a building, it's going to have gravity, mg, pulling down on it, and it's also going to have this bv thing slowing it down. So this is reducing the net force acting on it. Okay, so here is our equation that we want to start with. If we're interested in terminal velocity, that is where the acceleration goes to 0. You'll notice you'll continue speeding up as v increases, then this net force decreases, and you'll get a point where you get 0 acceleration, where these two things are equal to each other. So where gravity is balanced with the drag force. And if we solve for v in that case, you just get mg over b, so we could call this vt. Here is a nice little equation. You should probably jot it down for terminal velocity under the assumption that the drag force is proportional to velocity as opposed to velocity squared. Okay, well that's not so bad so far, but now let's look what happens to our good friends, the kinematic equations, when we try to derive those in a situation where we have drag. So we don't have constant acceleration, so we can't use the old kinematic equations that we're used to. And we can derive velocity as a function of time, starting the same place we did for terminal velocity. Again, just assuming it's proportional to v, the drag force. And so we have this equation here. Now we can rewrite the acceleration. Here I don't want the acceleration to be 0. I want to know my velocity at any time, not just after terminal velocity. So I can write this as dv dt. And then if I want to collect my v over here and move things around a bit so I can take this integral, If I divide everything through by m, I'm going to get g minus b over m times v equals dv dt. Okay, not too bad. Then I can multiply the dt over there, divide by all of this stuff, and I'll get dt is equal to dv over all of this junk. And just to make this integral easier to evaluate, I want to get rid of that b over m in front of the v. So what I can do is I can multiply both sides by a negative b over m. And then if I multiply this side by a negative b over m and distribute that, so over here it's going to be, in the denominator, it's going to be m over b. So I've got negative b over m dt equals a dv all over mg. Actually, I want to write that second because that's going to be our negative now. Go away, mg. Okay, so we're going to have v minus mg over b. So now I collect all my constant stuff over here, and things are looking good. Now I can integrate both sides. If I assume that my velocity is 0 at time 0, so I'm dropping this object from rest, then I'm going to integrate from 0 to t and from 0 to v. Over here that just gives me a t, so I have negative bt over m. And here you get to do this wonderful integral, and you end up with the natural log of v minus mg over b evaluated from 0 to v. And we'll come back up top here because we ran out of room down there. So we've got this. I'm going to plug in v for v and then 0 for v. I know that's not the best way to do integrals, but we'll beg forgiveness from the mathematicians. Alright. Okay, so we got this, and then we subtract natural log of 0, so this just becomes mg over b here. Okay, and then if we are subtracting natural logs, that's the same as dividing inside the argument. So we get this guy, natural log of a big fat v minus mg over b all over negative mg all over b. And now we just have to simplify things a bit, right? First of all, let's take e to the power of both sides to get rid of that natural log. So we'll get e to the bt over m. That natural log goes away. V minus mg over b all over negative mg over b. And then if I multiply this guy up over here and solve this for v, I'm going to have v equals mg over b, so that's this term that went over there, and then this guy multiplies up, so minus mg over b times e to the negative bt all over m, and we are almost there. We can just factor out this mg over b thing. So we get mg over b times 1 minus e to the negative bt all over m. And there you have it, velocity as a function of time with drag force proportional to the velocity. So not quite as nice as v equals v naught plus at, right? That was a little simpler, but there you have it. And you notice as t gets large, then this thing goes to 0, and so we're just left with mg over b, which is the terminal velocity that we saw earlier, which is what should happen when t gets large. Alright, so to get the position as a function of time and the acceleration as a function of time, we can just take the integral and derivative of this guy, and we end up with these wonderful equations here. There is our displacement as a function of time, the velocity one that we just derived, and there is acceleration. And you notice as t gets large, this guy goes to 0, so you end up with an acceleration of 0. When t is small, when it's close to 0, this guy just becomes 1, and so that is our initial acceleration, which is g, and so that is all well and good of what we should expect. You can go through a similar derivation where you have it proportional to v squared instead of v. You start out just the same. It's just at where, yeah, I mean this is going to be a v squared here, this is going to be a v squared, and this is going to be a v squared. So that's going to end up changing your integral, and you end up with more nasty stuff. You end up with hyperbolic functions, but there you can fit it. And let's look a little more closely at the difference between velocity as a function of time if you have the drag proportional to v versus proportional to v squared. If you plot those two things, I plugged in just random values for m and b. I think I plugged in 1 and 2 for those values. Anyway, you'll see that if it's proportional to v squared, you end up with more drag, and so you end up topping out at a lower terminal velocity. If it's proportional to v, this keeps on going, and if you look at the equation here that I plotted, this guy is heading all the way for 19.6, so this guy is going to keep on going all the way up there until 19.6. So you end up with more drag, obviously, if it's proportional to v squared. If you have the same b value and the same mass, then this is kind of how things work out. What's interesting, though, is if you assume different b's depending on the models for the drag. If we assume that they're both heading to the same terminal velocity, they're both going to approach this 4.4 thing. In that case, then you actually get to your terminal velocity a bit quicker if your drag is proportional to the velocity as opposed to the velocity squared. This hyperbolic tangent, by the way, tends to 1 as x gets large. I guess these are t's, right? But I just use x's. So there's some terminal velocity fun for you. As far as an example, the types of problems you're going to have to do for your homework are kind of long and nasty, and I'm not going to take the time to work through something that long. So we will do a simpler, easy example, and then if you need help in class on the hard problems, I'll be there for you. Alright, so here we've got terminal velocity for a 65 kilogram person is 56 meters per second. What is the value of b? And by b we're talking about this same b coefficient in our drag equation here, again with a negative sign. So in this case we can just jump to our terminal velocity expression, mg over b. We're going to solve this guy for b. This obviously is a very simple problem. We end up with this. We plug in the mass of 65, the acceleration, the terminal velocity of 56, and we end up with 11.375. We'll round it to 11.4. The units of b are something good to talk about. If you look at what quantities we put in here, that's going to be kilograms for the mass. G is an acceleration, so that's meters per second squared, and then this is velocity, so that's meters per second. That's kind of ugly. We can simplify this a bit. A kilogram meter per second squared is a newton, so you could simplify this to newtons per meters per second. Or you can cancel out the meters, and you can cancel out one of the seconds. So this is also equivalent to kilograms per second, which doesn't really have a good intuitive meaning to me, but anyway, those are the units for your b coefficients if you have linear drag. Okay, see you next time.